Reaction rates are the time it takes for a reaction to happen. There are different things you can study through reaction rates, and so we're going to go over the basics now, and then we'll go through more with other sections. So first, kinetics. Definition. It's literally related to reaction rate. So as you can see here in the definition, it says reaction rate, and so we're seeing how much of a reactant, typically molarity, but again, depends on what it is, and we're seeing how much product is made, or we're focused on just product made. It depends on the situation, it depends on the experiment. It is always per some unit of time, so it depends on what unit we're using, usually seconds, but it could be other time too. As a reminder, per for units means slash, like miles per hour is miles over 1 hour, so just remember that for per. And we use different units, so we can have the delta symbol or we can not have the delta symbol. The delta symbol is from one situation to another situation. It's a change versus not having the delta symbol, then it's just chilling at one time. Here is an example, okay? So this is just a random reaction, okay? And so we're going to go ahead and write the example rate. You can see here we have negative delta B, the concentration of B, divided by the delta T, how much time spent, and the coefficient 3 on the bottom. So if there is a coefficient, it will always be on the bottom, and this general system is always how it's written. There is a negative sign because this is a reaction going from left to right, and so we are consuming the B substance, and so that's why the negative sign is there. We can write the other components of this reaction to write the rate. So for example, the rate is going to be the same for all of these because they're all balanced in this random example. And so I can also write it for A. And so for A, because A is being consumed, it's going to be negative. We're going to have a change in the concentration of A, whatever concentration changes over time. And then we have the delta T on the bottom. Now, there is an invisible 1 coefficient here, so that means there will be an invisible 1 over here. So again, you just make sure to have the coefficient on the bottom. So this is writing the rate based off the reactants, but you can also write it based off the products. So they are all equal to each other. Because product is being made, we're going to have a positive rate. You don't have to put the plus sign because, it's assumed it's positive unless you have a negative sign, but I'm putting it anyway. And then we have our change in the concentration of C, and then we have the change in time, and then we need the coefficient, which is 2, down here. So this is generically how you would write the rates. Okay, so here's an example problem where we're going to apply this. Now I will add a little note. I'm going to teach this slightly wrong, mainly because students are not used to one thing replacing 2 variables. So that's why it's going to be slightly wrong. I'll explain what I'm doing, why it's wrong, but it doesn't matter as long as you show your work in some way. So it doesn't have to be exactly mine. If you want to follow it the correct way, I'll explain the correct way too. So first I'm going to explain it the regular way. So here's a problem. We got an equation. We have a rate of formation, aka how much nitrogen is being made. So we have a rate of 0.27 moles per second. So we can determine the rate of water formed. We can determine how much oxygen was used up. We can determine how much ammonia is used up. So all of those things can be calculated. And so first you need to write the rates based off the example I went over. So here we have water, because that's what we're trying to solve for, and then you want to put delta T here, and then there is a 6 here because of the coefficient 6. Then we are writing the nitrogen one because we have the values for nitrogen. So N2 is over here, and then delta T, and then there's a 2 here. Now here's where I'm going to do something slightly wrong. Mainly, again, because students get confused to replace something when it is 2 variables instead of just 1, because technically the 0.27 moles per second is this whole entire thing. But students get thrown off by that for some reason. And so I just show, okay, just cancel out some stuff. You could cancel out delta t, right? On both sides, because it's technically the same thing, delta t, right? And so I can isolate the water part because that's what I'm trying to solve for. And so when I isolate that water part, I now have the delta n with the 6 and the 2, and then I could just plug in my value. So that's just literally plugging in this thing, and I get my answer at 0.81 moles per second. Okay, so again, I said that this is the incorrect way, mainly because students get confused about two variables is a thing you're solving for, you know, and you're replacing a number with two things at the same time. And so let me talk the process of why you don't have to cross this out. But again, the crossing out thing just helps for those that like to replace a thing with just one thing. So you still have the same setup. So you still have your delta H2O change delta T equals delta N to 2 delta T. I forgot the 6 over here. And so the only difference between the actual way versus the way that I showed on screen is, okay, I'm going to multiply both sides by 6, so I can get rid of this 6 and just put it over here. And when you're replacing the 0.27, you're replacing this whole thing. So let me circle this whole thing right there, because that whole thing is technically 0.27 molar per second. So really it's 6 divided by 2 multiplied by 0.27 molar per second. So in case you're like, why am I replacing the whole thing? Well, the seconds is the delta t, which is a 1 technically, because 0.27 m divided by 1 second. And so that's why this is the actual proper way of doing it. But students, again, confuse plugging in a thing to be two different things. So I just say, just cross this out and then pretend it's like normal math. Because, again, some students get confused by that. So, again, I showed the wrong way, and now I showed the correct way here. So you do whatever works for you. So you can apply this for any part of the reaction. If you're given one thing, you can find the rate of everybody else. So you can see how much ammonia was used up in this reaction. So you do the same setup. As a reminder, the negative sign means it's being used. And so I'm showing, again, the incorrect way of doing it for those that get confused about the thing that's replacing two things. And so then I get ammonia by itself. The 4 has been moved, and then you just plug and chug and you get your value. So again, the negative sign is purely showing that it is being used up. There's no negative concentration. It is the amount that is being used in this reaction. So here are 3 your turn questions. So the first one is multiple choice, and then the other 2 is practice of the stuff we learned. So go ahead and pause this video and then go ahead and watch the answers once you've tried it. Okay, so it is B, and I'll show why. So we have our delta B divided by delta T, and then we look for the coefficient, which is a 3, so that goes on the bottom. And then we do the same thing for C. So I show the concentration of C divided by delta T. The coefficient is 2 here. And so in order to see the disappearance of B, we got to get this part of the equation by itself. As a reminder, the rates are equal because it's a balanced equation. And so in order to get this rate by itself, you need to multiply both sides by 3. And so you have your concentration of B divided by delta T. That's the rate of B. And then we have the concentration of C, and then delta T. You have the 2 over here, and then the 3 over here. I also forgot the negative sign, but whatever. The rate of disappearance is negative, so you could just put that there. Put that there. And so you could see it's 3/2 of C as C appears. And so that's how you can get this answer. So for question 2, it's just practicing writing the rate. we have our 2A, 3B. You want to make sure the coefficients are on the bottom. You want to make sure the reactants have negative signs. You want to make sure the products are positive, and that's why they're written the way they are. And then for number 3, we have combustion of methane. So we have a reaction. And so which reactant has the greatest rate of disappearance? Well, it's the O2. Here's our 2 reactants over here. And there's a 2 in the front of O2. So for every 1 mole of CH4, 2 moles of O2 are going to disappear. Hence why oxygen would be the greatest rate in comparison to the methane. There are various things that can affect reaction rate. The important thing to know is why they affect it. So you need to think of the reasons. These are very easily MCQ or FRQ questions. And so temperature is obviously going to affect the rate. If we increase that temperature, that means we're increasing the rate because we're increasing the kinetic energy all of the particles have. When you increase the kinetic energy, that means you're increasing the successful collisions those particles can have in order for that reaction to happen. So, again, you have the kinetic energy increasing, and so therefore you're increasing the successful collisions in order for the reaction to occur. So that's why when you increase temperature, it's going to increase that rate. You have reactant concentration, so the amount of reactants you have. If I increase how much reactant I have, then I'm increasing rate, because if I have more reactants in a system, then that means those reactants can collide more, and so there will be more successful collisions to make a reaction happen. Then we have surface area. So imagine you have fine powder versus solid, right? And so if I increase the surface area, so if I think about like a tablet versus a powder, the tablet has a reactant inside of it that's not reacting right away, versus everything's a powder, then all of it can react if it's touching the other thing that it's going to react to. So if I increase that surface area, that means I'm increasing the exposure of those reactants and therefore increasing more successful collisions in order to make the reaction happen, aka increase that reaction rate. For catalyst, this is going to be section 511, but in general, if you add catalyst, it will increase the rate. I'll explain more in detail in section 511. And then the environment itself. The environment itself, it honestly depends. Because are you in an acidic environment? Are you in a basic environment? It just really depends. Here is a graphic on how to make chemical reactions faster. It's a great graphic. I have this linked on the slides on the classroom website, so you can feel free to look at it. But pretty much what you're noticing is the majority of the time you're just increasing the successful rate of the collisions happening. So those reactants are hitting, successfully in order to make whatever products you are trying to make. That's pretty much what you're doing for the most part. You need to know how to recognize a reaction rate graph and also be able to draw it. So you want to make sure that you know that time is always on the x-axis and the concentration is on the y. You'll have reactants and products. Sometimes your reactant line is going to be several different reactants. They'll show several reactants on separate lines because they want to show specific species. Same with products. If there's multiple products, you might have multiple lines. Or for this particular generic graph, they're just all on the same line. But in general, usually you separate each species into its own line. And so you start off with some amount of reactant, as you can see here. Again, you're usually given this information, but you should also be able to generically draw this. And sometimes you start off with some product and sometimes you don't. So you want to start where you need to start based off what the problem gives you. And then over time, reactants are being used up, some products are being used up. But if it's a reversible reaction, you will always have some reactants and products. There is a point to know is the equilibrium. As a reminder, equilibrium is a reaction that goes forward and reverse. So reactants are becoming products, but products are also becoming reactants. And so when you reach that equilibrium point, that means the rate of the forward reaction, so in that case reactants to product, is exactly the same as the rate of the reaction backwards, going from product to reactant. So that's the point when they are the same in terms of rates. On the graph, when you reach equilibrium, this bottom line here and this top line are going to be completely horizontal. So right now you can see the reactants have reached a horizontal line, but the products are not quite there yet. Eventually the products will also be a horizontal line. When every single line on the graph is horizontal, that is going to be equilibrium. Now, reminder about slope, like just in general, right? So slope is change of y over change of x. So for this graph, that would be the change of concentration over the change of time. And so there are two different slopes. You can talk about instant versus average. And so if I were to think of the instant rate, this would be a calculus-based problem, and we're not going to do that for this class. But if you're doing the average rate, you can average between two different points, and you should be able to do that if you're given values on this graph. So if you have, again, 2 points, you can calculate the slope, and then by calculating the slope, you would get the rate. So we can actually use Stoich with reaction rates, and so I'm going to show that. I'm going to do an example twice, showing one way and another way. So here's the example we're going to do. And so we have 2 seconds and the concentration has decreased for the calcium hydroxide by 0.2 molar. And so what's the appearance rate of water? I can first do the reaction rate stuff that we learned in this section. And so I can go ahead and just do that. So I have the concentration of calcium hydroxide divided by the time it took, and then the 3 is from the coefficient that's on the bottom, and so I calculated that. As a reminder, that negative sign is just to show disappearance. It doesn't mean anything math-wise. I could just straight up ignore it if I'm trying to calculate the rate for the water. And so here's my rate of water. So remember that rates are equal to each other. So since it's 0.03 molar per second, then I got my water one. And so I could multiply both sides by 6 because the coefficient from the water in the balanced equation, and then I got my rate right there. So there we go. Now the other way of doing it is the Stoich way. So first you have a rate. So I calculated the rate, just 0.2 molar divided by 2 seconds, and I have a rate right there for the calcium hydroxide. And then you could just use the balanced equation, and the balanced equation will cancel out the moles, and then I got rate. So you can pick whichever way you like. Here is a very common problem that's on a FRQ. It can be an MCQ if the numbers are very easy and you don't necessarily need to do it on a calculator. But in this case, you actually do need to use a calculator for this one. So you have a data table, you have a balanced equation, and so you need to calculate the rate of appearance for oxygen. So go ahead and try this out. I do have a hint on the bottom. I will also mention one more hint in a few moments. So try this out, pause the video, and then if you get stuck, I'll say a hint. Okay, if you still need a hint, you have the concentration and time of the reactant or one of the products. And so you can calculate the rate of one of them. It doesn't matter which one. You could pick and choose whichever one you feel like. And then as a reminder, the rates are equal to each other. So then you do the same math as we've done in a previous problem. Okay, so I'm going to go ahead and go over the answer now. So here we go. So the first way, you could just do it the reaction rate way. So reminder that everything is equal to each other. So here I show that they're all equal. And then I picked N2O5, but it doesn't matter which one you use because they're all equal. So in order to use N2O5, I just plug in the values. Remember, delta T is just change. So I'm changing from the 240 seconds to the 600 seconds. And so I just plug and chug with my delta, and then I get my rate. And then I just make those equal to each other. And then notice there's no coefficient on the oxygen, so that's just the rate of the oxygen. So there we go. So the answer is exactly the same, which is what I had covering right there. Cool. So the other way of doing it is the, again, the coefficient Stoichi way. So first you can just, again, the big negative sign is just showing, hey, it's disappearing. It doesn't matter. It's just showing it's disappearing in terms of math anyway. And so I have calculated the N2O5. We have, as a reminder, M is moles per liter. And so then I could put moles on the top, liter per second on the bottom. I can cancel out my moles of N2O5 specifically because I want to get moles of oxygen. So those guys cancel out. And so then you are left with the moles of O2. And then when you have moles of O2, moles per liter, well, that ends up being molarity. And then you're done. So you just plug in that divided by 2. And then it's the same thing. So you decide what you want to do, again, in terms of how to calculate these. And that's it. All right. Bye.